What's up? In this video I'm covering the MLP-Mixer, an all-MLP architecture for vision, a newly published paper by the Google Brain team, and I'd give it an alternative title, which is MLP is all you need, because as you'll soon we went a full circle and we used to use MLPs, the multi-layer perceptrons, to solve the vision tasks, and in 2012, we had the ImageNet moment with the AlexNet, which basically showed that it's much wiser to just use big convolutional neural networks with a lot of data and compute to solve the vision tasks. Finally, we started using transformers. We started with the Vasvani transformer in 2017, and then in the last year we had vision transformer, which showed that with lots of data, and it used like the JFT 300M dataset from Google, the proprietary dataset, and with 300 million data points, it showed that it can learn really nice representations and even achieve better results than CNNs. So finally, back to 2021, this paper came out and showed that by just using these simple multi-layer perceptrons in a clever way, arguably, you can achieve similar results, and compute-wise, you can be even a bit better, and throughput-wise as well. So yeah, let's see. So basically, the main thing is this paper doesn't try to achieve the new soda. It just shows that we need to maybe investigate some other research paths, which may lead us even further. So this paper is a good step towards that direction. So they show that with simplicity, they can still achieve great results. So who knows, a couple of papers down the line, what this may evolve to. So having said that, let's dig into the paper. So first things first, they say here, the mixer relies only on basic matrix multiplication routines, changes to data layouts such as reshapes and transpositions, and scalar nonlinearities such as Gaussians, as we'll soon see. So that part associates me to Bitter Lessons by Sutton, which is a blog you should check out by Richard Sutton, which basically, and I'll link it down in the description, but it basically says that the model that stand the tooth of time are those which are simple and can leverage the available computation of the time. And so this paper is super simple, and you can see they even linked like a code snippet implementation of this paper at the last page, which kind of tells you all about it. So it's basically 20-liner, and that's awesome. So that's simple and achieves nice results. So yeah, I like it. That's the part I like about this paper. The architecture-wise, so they just have these channel mixing MLPs and token mixing MLPs. So the token mixing MLPs basically attend across the image, so the spatial extent, they attend the tokens, the patches, and the channel mixing ones just focus on a single patch, and they kind of process the channels, hence the mixer name. So they are mixing between processing channels and processing over the spatial extent, i.e. over the tokens or patches. So here is the architecture, fairly simple, resembles the vision transformer a lot. So if you haven't checked out, I've covered the vision transformer in my previous video. I'll just link it somewhere here. The architecture is very similar to the vision transformer. So you just take the input image, you split it into patches, as you can see here. You flatten that out, as you can see here, and then you just unroll all of these matrices into vectors, and you use a single fully connected layer here, which is shared across all of these patches, and you just project them into some new latent representation vectors here. Then they stack n of these mixer layers, which we'll soon see what they are, but like they ended up with global average pooling and a linear classifier on top of it. So it's a super simple architecture. Mixer contains the part that mixes. So this is the token mixer part, this here, and this is the channel mixing part, this part here. So before digging into those, so just let's see what MLP is. MLP just consists out of two fully connected layers and a Gaussian nonlinearity in between. Okay, so super simple. If we ignore the transpositions here, what they semantically do here is they just take the column here and they apply the first MLP, the MLP1, they applied on this column. So they'll project this column into some other subspace, and they'll just take the same MLP, take the second column, project that one into another space, and basically you arrive at a new subspace here, which has the same dimensions. So it's C and S here as it was here. So they preserve the dimensions, and that's the legacy from the transformer architecture. So basically, if you take a look at the CNNs, on the other hand, you usually have the spatial extent usually goes down. You have this pyramid-like structure where the spatial extent goes down, where the number of channels increases, usually twofold. That was at least some heuristic people used to use. Doesn't mean it's the best one. And here we're preserving dimensions. So the second thing they do is, again, ignoring layer normalization and skip connections, they just take the row-wise, they just apply these MLP2 network to like row-wise onto this matrix, and they achieve some new representation, and they just repeat this n times, and that's it. That's as simple as that. So skip connections are just like the Resna paper introduced those, and the transformer used those as well as the layer norm. So the original was fine transformer used layer norm. So I guess a bunch of those are just legacy artifacts. What's new here is they are not using CNNs, they're not using the convolutional kernels, they're not using the attention, they're just using MLP. They took some of the legacy from the previous art, but yeah, and they showed, as you will soon see, that they achieve comparable results. And yeah, they say it here. Despite its simplicity, Mixer attains competitive results. When pre-trained on large datasets, so 300 million actually, it reaches near state-of-the-art performance previously claimed by CNNs and transformers in terms of the accuracy-cost trade-offs. Okay, yeah, maybe a small rant here. It's unclear from the paper why they're using GALUs, so it seems we keep using like these exotic activation functions without having a good reason why. Like for their defense, they have on one of the last papers, they do have the things they've tried and that didn't work, and which is really super and great. But I'd like to know why they use GALUs and why not use ReLU. I think those kinds of insights would be really useful. But what probably happened is they tried a couple of these, and they just took the best one, just a simple grid search over activation functions. But like more probably they just took it because some other paper used it, and that's it. But yeah. Second thing is, I mean, we keep on using these normalizations again without any particular reason. As far at least I don't see it. So like, why are we using layer norm and not batch norm or instance normalization or group norm? Like, there is too much tradition and legacy and taking something that worked, and there is too little theoretical explanations of why we're actually using something that we're using. And that's why we get papers like this, where after years of developing of CNNs and transformers, we show that, hey, we can just use MLPs, it's gonna work. Why are you complicating things? So yeah, a small rant over. Let's continue with the paper. I'll skip some of these details. For now, I just want to give you the bigger picture of the model for now. So first things first, similar to the vision transformer, they have they create a family of models. So they have the small mixers with 32 means basically the patches are 32 by 32 pixels. So that means you'll have less of those patches because the patch is bigger. And then they have 16 here, so then big models, large models, and finally the huge mixer. And yeah, just a bunch of different hyperparameters depending on, so basically as you go towards a huge model, you increase everything, and that's it. Again, skipping the details and focusing on the results. So, as you can see, when it's pre-trained, and this is the main takeaway, when it's pre-trained on smaller data sets, it's not going to have as good performance as the better model, as the more common CNNs and transformers, such as the big transfer model, the vision transformer. So as you can see, it's lagging behind a little bit here compared to BIT and VIT. But this part actually, I highlighted this part because it's actually a bit better, a lot better on VTab, which I think is more complex actually than the other ones. So that's kind of surprising. I'd like to know what this number is all about. And yeah, you can see the throughput is a bit better than the vision transformer. The compute is a bit higher, so it's hard to compare them, but it's definitely not a new state of the art. It's just comparable. You can see the perf wise it's there, throughput is a bit better, but then compute wise it takes more compute than the vision transformer, which is interesting. And yeah, but going to JFT 300M, you can see that now we have even better performance than the big transfer model, and it's comparable to vision transfer. NFNets are decently better. It's lagging behind NFNets, both in terms of performance, both in terms of throughput, and yeah, but this NFTNet takes a bit more compute. I'd like to see a comparison with the EfficientNet v2, which was recently published, and which showed that it's much better than NFNets. So yeah, I wonder why they omitted that part. Probably because they were already late into the paper writing. But yeah, I'd like to see the comparison with ENet v2. So those were some tabular results. Now let's see the charts. These are really interesting. We have the chart that shows the compute accuracy trade-off here. And you can see that the mixer is directly on the Pareto frontier. And what Pareto frontier is just a fancy word. Basically, that means that if you're at this point, you cannot increase one metric of interest without decreasing the other one. So that means you can't do this, because that means, that means you're keeping the accuracy constant, but you're decreasing the compute. Or likewise, you can't keep the compute and just increase the accuracy. You have to move across these lines where if you want to increase the accuracy, you have to increase the compute. Or if you want to decrease the compute, you have to decrease the accuracy. And that's just a trade-off. And a good thing and a really reassuring fact is that it's lying directly on that frontier alongside with NFNets and alongside with the vision transformer. So those are some nice results. The second chart shows us that as we increase the compute, so going from 10 million data points source to the full data set JFT 300M, we see that basically, and the full lines are the mixer models, the other ones are the big transfer and the vision transformer. So we can see, and what's interesting is that for smaller models, for smaller mixer models, it plateaus really quick, and it achieves results maybe a bit inferior to those baselines. But like when we go to bigger mixer models and large data regimes, we can see that it even achieves better performance at finally, like compared to this is, I think, yeah, vision transformer. So the encouraging thing is that the derivative here is positive, which means if we extrapolate, hopefully it's going to go towards the AGI. That's the promise of this model, obviously. Yeah, and jokes aside, it does seem to have like steeper like slope here than compared to the vision transformer, which is encouraging, which means that we can push this even further. So 2 papers down the line, we'll be seeing even bigger data sets and yeah, better performance. And I haven't mentioned this part, and it's just an implementation detail. The reason they use this linear 5-shot ImageNet top 1 instead of just using ImageNet top 1 is because it was really compute intensive, even for Google Brain, to train all of these, to fine-tune all of these models. So as a proxy, so they've just frozen the weights that come from the images, and they trained a small linear classifier on top of it and used that as a proxy to fine-tuning. But just an implementation detail, as I said. The main takeaway here is that it seems that MLPs have even greater potential than vision transformers, and that's exciting. 2 more curves here. Again, compute versus accuracy. You can see mixer is pretty decent on this part of the spectrum. So when we have a bunch of compute, it's pretty decent and comparable to the vision transformer. As we go on the lower part of the spectrum, of the compute spectrum, it seems to lag a little bit behind the vision transformer, but yeah, it kind of converges here. And we saw the similar behavior with the vision transformer compared to CNNs. Only in the big data regimes we get really high performance out of it. Similarly here, throughput and accuracy, it's on the frontier. Here they just have some additional tabular data, but all of the main takeaways were pretty much in those charts I already described. Regarding compute, they say it here, we may scale the model in 2 independent ways. So increasing the model size, the number of layers, blah, blah, blah. And during the pre-training, and the second dimension is increasing the input image resolution when fine-tuning. So those are the two things they had as in their toolkit. And as I said, it appears that mixer models benefit from growing pre-training dataset size even more than the vision transformer. Nice. Finally, nice visualizations here, and that's the end of the paper. Basically, first of all, let me explain you what these patches represent. So if you have the input image, and let's draw it like this, and it's got some patches. I'll draw it like 4 by 4, but it's usually much more. It's usually 14 by 14 or something like that. And what it does, so if you take this single patch, what it does is basically, imagine we have 14 by 14 of these patches. And so this thing here basically means that if we take this and flatten it out like this, so we have S here and C here, and that was the usual representation we used in the beginning of the paper. So this will be 14 by 14, and the number of channels doesn't matter now. So basically, this thing here is the weights which attend to all of the elements in this column. And if you remember, so these are the tokens. So that means a single pixel here will attend to a single patch here. So that means if you have something like this, let me zoom in a bit, something like this, that means that particular fully connected layer is going to attend a lot to this part, because the red, let's assume red is some positive number, so it's going to have to attend this part of the image with the positive weights, and it's going to attend this part of the image with the negative weights, hence the blue part. Similarly here, you can see that the blue part, that means we're going to attend this part with negative weights and this part with the positive weight. So, and another interesting detail is that you can see there is a lot of symmetry here, and they've intentionally arranged all of these like that. And also, if you take a look at the y-axis, the frequency kind of goes up. So these are the low frequency components. This is like the DC component. And then we have the high frequency components here. By the way, this is the first MLP layer. This is the second token mixer layer. This is the third token mixer layer. So as we go here deeper into the network, we can see that the patterns become much more complex, higher frequency ones than here. And the idea why they did this is because usually when we analyze CNNs, we can notice certain patterns, and they mentioned the Gabor filters, which is just a you get those by a combination of Gaussians and sinusoids, and we see similar structure in the lower layers, but when we go deeper into network, we get something that we still can't discern. And it'd be nice to kind of analyze this and do some mathematical approximations here to understand how we can model these, and maybe we can take some intuition further from this and devise better models once we know what this thing is modeling. So yeah, but it's I guess future work for these authors. Now let me go ahead and explain a couple of those details which may be important to you. So first of all, let me start with this. So I mentioned that they are sharing weights. So all patches are linearly projected with the same projection matrix, and that helps saves up the memory footprint. So that's important. And they are also sharing the across the columns and across the rows. So that's the token mixing part and the channel mixing part. And let me just decrypt these equations for you. So basically, we take that input matrix, which has dimensions S times C, if you remember, and they applied normalization, and this weight matrix just represents the first fully connected layer of the MLP. So that's this one here, that's the network. And then they have a nonlinearity, which is Galileo, so that's this one. Finally, they have the second weight matrix, which represents the second fully connected layer, so that's again this one here. And finally, we have plus with the input, which is basically the skip connection. And then they just repeat this and apply the second thing is basically so this is across channels and this is across. So that means it's a token mixer, and this part is across basically. So let me draw the matrix here. So this is S, this is C. This goes across channels, so that means it's attending a bunch of different tokens. So it's a token mixer, and here we go across S. So that means we're doing channel-wise mixing. So these are the two equations I wanted to explain. Okay. They mentioned that tying across the channel mixing MLP, so keeping the same network here and here and here makes sense, because you want to do the positional that encodes that kind of enforces the positional invariance, because whatever you learn here, you want to have a pattern that's generalizable to all of the other spatial locations. But you usually don't constrain. You usually don't take the network like the MLP and constrain it to be the same across the columns. So that's what they mentioned, and they actually tried both things. They figured out that just tying it doesn't hurt the performance, but it saves memory, obviously, because you don't have to have C MLPs. You can have just one single MLP and just apply it C times. But again, there's just thing. Like, there is nothing theoretically guaranteeing that this is a better choice. It's just a experiment. Important detail is that it's not using, so Mixer does not use position embeddings, because the token mixing MLPs are sensitive to the order of the input tokens and therefore may learn to represent location. So this is a direct let's make a direct comparison with the transformer. So transformers have, as you may recall, so these are the patches embedded into the latent space. And what the transformer does is, let's take this token, for example, is going to attend all of the other tokens. So we're going to create those keys, queries, and value vectors, and we're going to attend all of the other tokens, and we're going to form those alpha coefficients, basically the attention coefficients, and we're going to sum them up. And because we're summing them up, we are losing the positional information. And because of that, the original, the Vaswani paper and some in the successor papers basically had to add additional positional information. So that's kind of going to encode somehow that this is different. So maybe like this, and then we'll maybe have the second position encoded like this, whatever. You need some unique pattern that kind of uniquely identifies each of the positions. But here, because we have MLPs, we don't need to do that. And the reason is, if you take a look at the matrix, we have S here and C here. So if you have MLP, like the token-wise mixer applied across this column, you basically, because it's an MLP, so it's got a fully connected layer, right? So it's going to do something like this. It's going to attend all of these positions, and this weight here is some weight V11, and that's the first element of the output vector. Then the second element of the output vector will attend like this. Again, it's a fully connected, and it's becoming a mess really quickly, but you can understand that basically. Let me take another color. So basically this one here is going to be some W12. And you'll have a collection of these weights which are particular to this token here. So it directly learns that for that position, for that token, which corresponds to a certain position in the image, so this is the input image, maybe this is this token here, this patch. So these weights will learn how to encode information from this particular patch, and that's why they don't need to use any positional encodings. Hopefully that was clear enough. If not, let me know in the comments. I'll try to explain it further. Okay, so that was the detail I wanted to explain, and the final thing I want to mention is this here. Here is some dark magic here, cosine learning rate. I really wonder why are we still using these without having any theoretical justifications. Like a small footnote of why they use that particular schedule and not something else, like a simple linear schedule or even some constant learning rate schedule would be really appreciated. And again, following common practice, And I highlight common practice because we also apply fine-tune higher resolutions with respect to those used during pre-training. So what happens here is that basically people show that when you're training for like vision benchmarks, you pre-train on certain resolution, like maybe 224 times 224, and when you want to fine-tune, you actually increase the resolution, and that will help you boost your performance. So you fine-tune on 384 times 384, for example. And as I said, so I highlight the common practice because I'm not sure if we still have an understanding of why this is making things work any better. So we are just using the legacy ideas, legacy heuristics, and keeping them in all of the present research. And I guess, yeah, we sometimes have to do that because otherwise, like, the research will fall apart. You have to clinch onto something. But basically, it'd be nice when we had more papers explaining why these things work, and not just combining them like as black boxes. There is one more detail I want to mention, and we are done. Basically, because they are doing this upscaling during the fine-tune process, they somehow have to adjust the weights of the MLPs. So the reason that is because, if you remember, so the input image can be represented as S times C, and because the token mixer basically attends across the number of patches, when we increase the resolution, so when we increase the resolution, but we keep the number of the size of the patch the same, that means we're going to have more of these patches. So that means S goes to S prime, which is a bigger number, and that means this thing won't fit into the previous MLP, which had a certain bandwidth. So it could attend like this. It was smaller. So now we have to kind of take the weight matrix of that old MLP, and we need to initialize this new weight matrix, which is bigger somehow. And what they did is they just took these and stacked them blockwise here. And that was the initialization method they used to fine-tune the models. So yeah, just an engineering detail. Thought it's interesting and important to mention that there are a lot of these details that go into making this thing work. And the reason this works is, if you think about it, if you now multiply the input vector with this new matrix, this thing is basically going to tend to the first part, and this thing is basically going to tend to the second part. So it's like you're applying these in parallel, and so that seemed like a sound way to initialize the new weight matrix. So that's the main reason they did it like this. Hopefully you found this video useful. If you did, leave a like, share the video, and see you next time.